Okay, so in this section, we're going to talk about exponential functions. So an exponential function, the general form of that is going to be f of x is equal to a to the x power, where a is bigger than, in this specific example, we're looking at when a is bigger than 1. So here we have f of x is equal to 2 to the x. So again, if we don't know what the graph looks like, we can always draw an x or write down an x and y table and plot points. All right, so I like to plot points that are around 0 because that'll give me information about the right side of the graph as well as the left side of the graph. So I'm going to pick -2, -1, 0, 1, and 2. Okay, and then again, our y function is going to be 2 to the x. Okay, so now let's just input that into our uh, function here. So we have 2 to the -2, 2 to the -1, 2 to the 0, 2 to the 1, and 2 to the second power. Okay, so let's go ahead and evaluate that. So 2 to the 2 power is going to be 2 times 2, which is 4. 2 to the 1 is 2. 2 to the 0, believe it or not, is actually equal to 1. And then 2 to the -1, if you look at your algebra formula sheet, I can rewrite this as 1 over 2. And this one as 1 over 2 squared, or 1/4. Okay. Now I just plot these points. So we have, see here, -2 and 1/4. So it's going to be down here somewhere, right? So here's -2, -1, 0, 1, 2. This is 1, 2, 3, 4. Okay. So -2 and 1/4 is really close to the x-axis. Then we have -1.5, so that's right here, halfway. And then we have 0, 1, which is right here. Then we have 1, 2, which is right here. And then we have 2, 4, which is up here somewhere. Okay. All right, so when we connect the dots, we're going to have something that looks like this. Okay. All right, again, it's just a sketch. Does not do perfect. All right, so this is an exponential function graph. So it's um, goes up kind of like a roller coaster, okay? And it goes pretty fast, significantly. So in this case, okay. All right, so again, let's describe this exponential function. The domain here is going to go from -infinity to +infinity. All right, so that's our domain. Or you can say this capital R, which means all real numbers. Right? The range, notice, is starting from 0, so the bottom of that, okay, graph, and going all the way to infinity. So 0 to infinity. Again, we just have parentheses there, right? X-intercepts, there are no x-intercepts. Y-intercept is at 1, okay? Um, or you can say at 0, 1. The horizontal asymptote, so the horizontal asymptote is at the x-axis. Is at the x-axis, and that's represented as y equals 0. Right? So again, this line gets really, really close to it, but never touches it or crosses it. Other. Well, notice this graph is increasing like a roller coaster. You're going up, right? You're on a roller coaster, you're going up, and then you go down. So this is an increasing function, right? And it's smooth. There's no holes or anything like that. There's nothing sharp points or anything. So it's a smooth graph, which is great when you're going on a roller coaster. All right. And it's also continuous. So continuous means you can graph or draw the graph without lifting up your pencil. So at any point you have to lift up your pencil to draw the graph, that means it's not continuous anymore. So again, it's continuous no matter where, you know, it continues from -infinity to +infinity. And it's also called one-to-one. What does that mean? So in order for a graph to be a function, it has to pass the vertical line test, right? So in order for this particular function to be one-to-one, then it has to pass the horizontal line test. So that means we would draw a horizontal line across and see if it only crosses at one time. If it does, then it's one-to-one. So that's what they mean by one-to-one. It's just instead of vertical line test, you use a horizontal line test. Okay. Now, in order for us to do this next set of problems, we need to rethink our minds in exponential form. Okay, so what do I mean by that? Well, if I have 4, okay, I can rewrite 4 as 2 square, which is 2 times 2. Okay, if I have 16, right, there's a couple ways to do this. I can write it as 4 square, which is 4 times 4, or I can write it as 2 to the 4th power, which is 2 times 2 times 2, right? 2 times 2 times 2 times 2 times, not too many twos. Okay? And this one will be 4 times 4, right? If I have 25, I can rewrite that as 5 square. If I have 64, I can rewrite that as 8 square, right? Or um, I can write it as 2 to the 6th power. Okay, so again, this is 8 times 8, or 2, 2 times 2 times 2 times 2 times 2 times 2, 6 times. Okay, so why don't you try this one? How can I rewrite 32? All right, so again, 32 is equal to 2 to the 5th, which is 2 times 2 times 2 times 2 times 2. Okay? Now, another thing we need to remember is if we have, say, um, x to the negative 2, I can rewrite that as 1 over x squared. Or if I had x equals x raised to the negative 3, I can write that as 1 over x to the third. All right. If I have 1 over x to the negative, say, 4, and I want that power to be positive, then I move it up, and that becomes x to the positive 4. Okay. And again, if I wanted to make that 4 negative, I would move x to the 4 to the denominator. All right. So again, if I have 1 over x to the negative 5, if I want that power to be positive, I just rewrite it as x to the 5th. Okay, so in this case, for these next set of problems, we need to use this theorem. So if um, a to the u equals a to the v, then um, I can equal the powers. U is equal to v. Okay? So again, if I have the same base, right? This is a. If we have the same base, right, then we can just equal the powers and solve. So for example, um, if I have 7x equals 7 to the third, then the bases are the same. So my answer here, I just equal the power. It'll just be x equals 3. And that's it. Okay. If I have, say, 5 to the x equals 5 to the negative 6, again, we have the same base. So that means then our answer is just going to be x equals negative 6. Okay. So again, if the spaces are the same, then we can just equal the powers to each other. All right. So, um, so in this case, we need to rewrite those bases, right? Because obviously they're all not going to be the same, right? So we need to figure out, okay, how can we make them the same if possible? So let's look at another problem here. So if I have 3 to the negative x equals 81. So x there. 3 to the negative x equals 81, and I need to find the value of x. All right, so again, we want to match the bases. So we have 3 here. So it seems, that we need to change 81 to match it with 3. So in this case, we can rewrite this as 3 to the 4th power equals 3 to the negative x power. Okay? So now we have the same basis, so we can just equal the powers to each other. So that's negative x equals 4. Then divide both sides by negative 1. So x gives us 4. Sorry, negative 4. All right, let's try another one here. Um, let's say we have 5 raised to the x plus 3 equals 1/5. We have 5 raised to the x plus 3 equals 1/5. Okay, so again, for the first one here, we had 3 to the negative x equals 81. So again, we want to make the bases the same, so we need to rewrite 81 as 3 to the 4th. So now the bases are the same. We have 3, so then we can apply the theorem where we can just equal the exponents. So it'll be negative x equals 4. Then we divide both sides by negative 1, will give us x equals negative 4. All right, for the second one here, again, we need to make the bases the same. So we need to rewrite 1/5 as 5 to negative 1. Okay, so now we have the bases the same. So we just equal the power. So x plus 3 equals negative 1, and then solve for x, and we get x is equal to negative 4. So check, check. All right, so the best way to do this one is let's rewrite the 1 over 64. So that becomes 1 over 4 to the 3rd power. Okay? So we can also write 1, right? Because 1 to the 3rd is the same thing as saying 1. So I can rewrite this as 1 to the 3rd as well. Okay? So in this case, then, according to algebra rules, since they have the same power, I can combine them as 1 over 4 raised to the 3rd power. Okay, so then on the left, we got 1 over 4 raised to the x power. Now we have the same base, so x is equal to 3. That's our answer there. Okay, all right. Let's look at some more examples. So this one we have 4 raised to the x squared equals 2 to the x. All right. So in this case, what we want again is to have the same basis. So what we do is we're going to rewrite the 4 there as 2 squared. Well, that's also being raised to x squared. Well, remember, a power raised to a power, that means you multiply. So this is going to be 2 raised to the 2x squared. Right? And that's equal to 2 to the x. So now we have the basis to be the same. So now we just equal the powers, which is equal to 2x squared equals x. Now, again, some students are going to be tempted to divide by x, but you don't want to do that because you will eliminate one of your answers. So remember, we have a power of 2. That means we should have 2 possible solutions. So instead of dividing by x, we're going to move the x to the left, and we have 2x squared minus x equals 0. Then I can factor out an x, and that leaves us with 2x minus 1 equals 0. then set those guys equal to 0. So we get x is equal to 1/2, and x is equal to 0. All right, the next one here we have 9 is raised to the negative x plus 15 equals 27x. 27 to the x power. So in this case, we need to change both of them. All right. So to have the same base. So notice that 3 can go into 9 and 3 can also go to 27. So that means 9 I can rewrite as 3 squared. And then 27, I can rewrite that as 3 to the third power, because 3 times 3 is 9 times 3 is 27. So what do I do now? Well, again, this is still being raised to the negative x plus 15, and this is still going to be raised to the x power. So we're just going to include those. So we have raised to the negative x plus 15. And then this is going to be raised to the x power. All right, so again, the power to a power we multiply. So that's going to give us 2 times negative x plus 15 equals 3 to the 3x. Okay, now we have the same basis. So we have 2 times negative x plus 15 equals 3x, and then we solve. So to distribute the 2, we get negative 2x plus 30 equals 3x. Then we're going to add the 2x on both sides. So that gives us 30 equals 5x, then divide by 5. So x gives us 6. All right, so let me try to squeeze in one more problem here. And this one is dealing with the letter E. And don't get scared by that. So E, if you type it into your calculator, it will just be a number, 2.7. Okay, so E is equal to or about 2.7. So it's just a number, right? So E is about 2.7. It's just a number, just like pi. Pi is approximately 3.14. All right. So this number 2.7 is used, shows up a lot in math, so they represented that by that letter E. Okay, so let's say we have e to the 4 raised to the x power times e raised to the x squared equals e to the 12th power. Okay, so what do we do here? Well, first, again, a power to a power we multiply. So we get e to the 4x times e to the x squared equals e to the 12th power. So remember, if you have, say, x to the third times x squared, I can add them, right? If you have the same base, you can add the powers. So that'll be 3 plus 2, which is x to the 5th power. So it's the same thing for this. So I have the same base, so I can rewrite that as 4x plus x squared equals e to the 12th power. So now I have the same base, so then I just equal the power to each other. Okay, and then move the 12 to the left and then factor. So I'm going to rearrange this from biggest to smallest. So xr plus 4x minus 12 equals 0. Then I need to factor. So the factor is x plus 6 and x minus 2 equals 0. And then we solve. So x gives us negative 6 and x also gives us positive 2.